So if you take a bar of pure silvery tin and you hold it right up to your ear and bend it, it actually screams.
Yeah, it produces this really distinct crackling sound.
Right, like a crying noise. And it's not just some faint background noise either. It's a very visceral, tactile phenomena.
Oh, absolutely.
What you are hearing is the sound of the internal crystals literally fracturing. They're just rubbing against each other as the metal deforms.
Yeah, metallurgists actually call that the tin cry, and
Yeah.
it's completely unique to the crystal structure of the element.
Wow.
You're basically hearing the atomic lattice resisting the pressure you're putting on it. It undergoes what they call twinning, where the crystal planes just, shear and snap into new positions.
That is wild. And that's really just the start of how strange this metal gets.
Yeah.
There's another phenomenon called tin pest.
Right, the cold weather transition.
Yeah. If you take that same piece of pure tin and expose it to very cold temperature, say like a bitter winter night,
Yeah.
it undergoes this bizarre phase transition.
It's so weird to see.
It doesn't rust. It doesn't just get brittle. The solid metal literally rearranges its atoms and crumbles into this dull, gray, powdery form.
Just falls apart completely.
Exactly. And historically, people would just watch solid metal objects disintegrate in the cold, which gave tin this highly mysterious, almost, I don't know, magical reputation. People actually thought the metal was diseased.
The mechanics of tinfest are fascinating, though, because they highlight how sensitive the element is at an atomic level. When the temperature drops below about 13 degrees Celsius, the crystal structure shifts.
Okay.
It goes from a metallic phase, which is known as beta tin, to a non-metallic phase called alpha tin. And in that alpha phase, the atoms actually push further apart.
So it expands.
Yeah, the density drops by about 20%. Because it expands so dramatically, the material simply shatters itself from the inside out.
That is just incredible. Well, welcome to our deep dive into element number 50 tin.
Glad to be here.
We are unpacking a comprehensive document today, simply titled 50tin.pdf, and it explores the science, history, and philosophy of an element that, honestly, most people just associate with cheap soup cans.
Yeah, that's usually the first thought.
Right. But our mission today is to discover why this really modest, unassuming metal is actually classified as a Tier 2 civilization-critical material. I mean, the sources go so far as to call it the binder of civilizations.
It is a remarkable classification, really, because when we study human history, we usually focus on the heavy hitters, right?
Oh, for sure.
We talk about iron forging empires or gold driving global exploration or, silicon powering the modern era.
The famous ones.
Exactly. Those materials stand on their own. But tin operates entirely behind the scenes.
Okay, let's unpack this, because as I was going through the materials, I kept coming back to a really specific analogy. Tin is basically the bass player in a rock band.
Oh, I like that.
Right. Like, you might not actively notice the bass line while you're listening to the track, but the exact moment you mute it, the entire song just feels hollow. It completely falls apart. It's the sonic glue.
I really like that framing because the defining characteristic of tin, both chemically and historically, really is that it rarely dominates a system.
Right.
You don't build a skyscraper out of pure tin. You don't forge a usable tool out of it. On its own, it is simply too soft.
Because of the crystal structure we talked about.
Right. But when you introduce tin to other elements, it acts as an enabler. It improves other materials and allows them to achieve physical properties they could never reach independently.
Which brings us right to you, the listener. Because the only reason you are able to hear our voices right now, streaming through whatever device you are holding or wearing, is because of tin.
Absolutely.
Your smartphone, your laptop, your wireless earbuds,
Yeah.
they are physically held together by it. But to understand how we got to a point where a crumbling, crying metal became the foundation of global technology, we have to rewind.
We have to go way back.
Yeah, we have to look at the massive geological lottery of how hard it is to actually create this element.
We have to go all the way back to cosmic origins. Because tin was not produced in the Big Bang.
Right.
No, the early universe consisted almost entirely of hydrogen and helium. To get heavier elements, you need stars to fuse lighter elements together in their cores.
Right, basic stellar nucleosynthesis.
Exactly. But a standard star, even a massive one, cannot easily create element 50. The cosmic recipe for tin requires what astrophysicists call a chemically mature universe.
Which basically means the universe had to go through several generations of stellar life and death first, right?
Yeah, precisely.
You need older stars to die and seed the cosmos with medium-weight elements, which are then swept up into new stars over and over again, building up the atomic weight.
That's it. Tin is actually forged in some of the most extreme cosmic events imaginable. We're talking about supernova nucleosynthesis, the explosion of massive stars and the incredibly violent mergers of neutron stars. In those specific environments, you have a process called rapid neutron capture. A lighter atomic nucleus is just bombarded by a flood of neutrons in mere fractions of a second.
So it's super fast.
Yes, much faster than the nucleus can radioactively decay, so it rapidly packs on mass until it becomes a heavy element like tin.
But wait, here's where it gets really interesting. Because I was looking at the science, and I struggled to wrap my head around the physics here. Scientifically, tin holds an incredible elemental record.
The isotopes, right?
Yeah. It has 10 stable isotopes.
Mm-hmm.
That is the highest number of stable isotopes of any element on the periodic table, from tin-112 all the way to tin-124.
It is entirely unique in that regard.
So my question is, if its nucleus is so fundamentally stable, why is it considered relatively rare and hard to find? I mean, compared to elements like iron or carbon or silicon, shouldn't a mature universe just be absolutely littered with it?
That is the central paradox of tin, honestly. You have to separate its nuclear stability from the statistical likelihood of its creation.
Okay, how so?
Well, having 10 stable isotopes simply means that 50 protons is what nuclear physicists call a magic number.
A magic number.
Yeah, it creates a closed, highly robust shell within the nucleus. So once a tin atom is forged, it is incredibly resilient. It holds itself together brilliantly without radioactively decaying.
So it basically survives forever once it's born.
Yes. But the process of being born, those specific apocalyptic conditions of a neutron star merger or a specific type of supernova that is statistically rare.
Ah, I see.
The universe has a very hard time setting up the exact conditions required to bake the tin nucleus in the first place. So while iron is produced abundantly in the normal death throes of giant stars, tin requires a massive cosmic anomaly.
And that cosmic rarity translates directly to geological scarcity here on Earth.
Absolutely.
You don't just find tin everywhere in the crust. It's primarily locked up in an ore called cassiterite, which is tin dioxide.
Right, cassiterite.
And today, major producers include China, Indonesia, Myanmar, Peru, and Bolivia. But historically, ancient civilizations had very, very limited access to it.
Extremely limited.
It was found in highly isolated pockets, places like Cornwall in Britain, the Iberian Peninsula, or these really remote parts of Central Asia.
And that localized geological scarcity is really the spark that ignited the first era of globalization.
How so?
Well, ancient civilizations often had access to plenty of copper. But copper on its own is deeply flawed for building a civilization.
Right, because it's too soft. If you make a pure copper sword and hit it against a wooden shield, the sword just bends?
Exactly. And let's look at the mechanism behind that.
Hmm.
Pure copper atoms are arranged in neat, uniform, crystalline planes.
Okay.
When you apply force to pure copper, those neat layers of atoms just slide right past one another. The metal deforms easily. And pure tin, as we discussed earlier with the screaming metal, is also extremely soft.
Right, they're both basically useless for heavy-duty work on their own.
But when you melt them together, usually about 90% copper and 10% tin, you fundamentally change the architecture of the metal.
You get bronze, the defining chemical equation of human history. Copper plus tin equals bronze. But how does adding a soft metal to another soft metal make something so hard?
It all comes down to atomic size. Tin atoms are significantly larger than copper atoms.
Okay.
So when you mix that 10% of tin into the molten copper, the tin atoms embed themselves into those neat sliding layers of copper. They act like microscopic speed bumps.
Oh, that makes sense.
They disrupt the uniform planes, causing immense friction at the atomic level, which prevents the layers from sliding past each other. That structural disruption is exactly what gives bronze its incredible hardness and durability.
That's amazing. So if we look at human progress as a tech startup, copper was the hardware, but tin was the rare, essential code needed to run the bronze software.
What's fascinating here is how tin symbolizes synergy. Unlike iron, which represents sheer isolated strength, you dig up iron ore, you heat it, you hammer it, and you have a tool.
Right, it's a one-man show.
Exactly. But tin symbolizes strength through partnership. It is inherently adaptable and cooperative.
And the chemistry actually reflects that broader theme too, right? The materials describe tin as a chemical peacemaker.
Yes, that's a great term for it.
Because it commonly forms two types of ions, SN2+ and SN4+, meaning it can easily choose to share either 2 of its outer electrons or 4 of them. depending on whatever environment it's in.
Right, it occupies this very unique middle ground between metallic and non-metallic behavior.
So it's chemically diplomatic.
Exactly.
But because cassiterite ore was so geographically scarce, those partnerships couldn't just stay on the chemical level. They had to translate to human behavior.
They forced our hand, essentially.
Yeah. Isolated groups of humans in Mesopotamia or Egypt couldn't stay isolated if they wanted bronze. They didn't have local tin. The necessity of this metal forced them to talk to each other. It forced them to trade.
Tin was really the original social network.
The original social network. I love that.
Because entire empires rose and fell based on their ability to secure access to tin or control the trade routes that moved it. We are talking about massive intercontinental networks stretching from the mines of Central Asia all the way to the Mediterranean.
And from the British Isles down into Europe and the Middle East.
Right. Ancient peoples were crossing oceans and punishing terrain, sharing ideas, languages, and technologies, all driven by the absolute necessity of finding this one elusive enabler.
It literally physically wove the ancient world together.
It did.
But that interconnectivity came with a massive vulnerability. The historical analysis in our sources notes that the disruption of those exact, sprawling tin trade routes likely contributed heavily to the Bronze Age collapse.
Yeah, because when you build an entire geopolitical system on a single, long-distance supply chain, you introduce extreme fragility. Around 1200 BCE, a combination of migrations, warfare, and potential natural disasters began severing those specific trade routes.
And without the routes, the tin stops flowing. Without the tin, you can't make new bronze tools to farm or weapons to defend yourselves. The civilization that depended on that cooperative metal just shatters.
It falls apart.
But that same ability to bind different materials together didn't just end with the Bronze Age. When humanity harnessed electricity, tin found its ultimate calling. It literally and physically binds our modern digital world together today.
Though it is worth noting that it binds our technology, not our bodies.
Oh.
Biologically, tin is almost entirely an observer. Trace amounts exist naturally in the environment and in organisms, but human life does not depend on it for DNA or bones or blood.
Wait, why is that? If it's such a great chemical diplomat like we said, why didn't biological life figure out a way to use it?
It mostly comes down to evolutionary availability and solubility.
Okay.
Life evolved in the oceans, utilizing elements that easily dissolved in water and were highly abundant, like carbon, nitrogen, and oxygen. Tin is relatively heavy and forms highly insoluble compounds in natural environments.
Oh, it just sinks to the bottom.
Pretty much. It just wasn't readily available in the primordial soup for biology to incorporate into essential enzymes, so it just sits on the sidelines.
Though the materials do make a very clear distinction here. Pure tin is benign, but when humans start forcing it to bond with organic carbon molecules creating what are called organotin compounds, it can become highly toxic.
Yes. Those are synthetic chemical combinations used in things like agricultural fungicides or anti-fouling paints for ships.
Right.
They're extremely effective at their jobs, but they can be highly disruptive to marine ecosystems and human health. But the pure elemental tin itself, it is mostly benign.
Which is probably why its first major technological leap in the modern era revolved around food, right?
Yes, canning.
Tin-plated steel gave us modern canning. Because tin doesn't rust easily and doesn't poison humans, a microscopic layer of tin bonded to steel allowed us to preserve food, store nutrients, and transport them globally without spoilage.
It revolutionized logistics and survival.
But the absolute biggest modern use, the reason it is civilization critical right now, is solder.
Solder is the literal glue of the digital age.
Let's break down the mechanics of why tin is so perfect for this. Because a modern printed circuit board, like the motherboard in a server farm, or the chip in your smartphone, has billions of microscopic electrical connections.
Billions of them.
And you need a way to physically bond those delicate silicon components together without, melting them into a puddle.
This is where tin's low melting point of roughly 232 degrees Celsius becomes its superpower.
Okay.
You can liquefy a tin-based solder to create the connection at a temperature that won't fry the surrounding plastic or the sensitive silicon chips.
Oh, that makes total sense.
Okay.
And because it's a metal, once it cools and solidifies, it provides both the physical anchor holding the piece in place and the electrical bridge that allows power and data to flow flawlessly.
It is the perfect bridge, and its future applications rely on that exact same cooperative nature. Advanced lithium-ion and sodium-ion batteries are increasingly using tin in their anodes.
Really? For batteries?
Yeah, the mechanism there is similar to its historical uses. Tin can alloy with lithium, so when a battery charges, the tin matrix can expand to hold a massive amount of lithium ions,
Oh.
which dramatically increases the energy storage capacity of the battery compared to traditional graphite. It is also becoming crucial in advanced photovoltaics, helping to bind layers in next-generation solar panels.
So I have to ask the ultimate hypothetical question then. If we woke up tomorrow and element 50 magically vanished from the Earth, do our modern lives just stop?
Well, humanity would survive physically. Again, our biology doesn't rely on it. But modern infrastructure would face an immediate catastrophic bottleneck.
Right.
The manufacturing of nearly all electronics would come to a grinding halt. You simply cannot mass produce circuit boards without tin solder.
And food preservation supply chains would be severely disrupted.
Exactly. The rollout of green energy, solar tech, and high-capacity batteries would suffer massive delays. We would have to undergo a massive, agonizing redesign of our entire technological foundation. Tin isn't the microchip, but it is the only reason the microchip can talk to the rest of the machine.
Which brings us to the modern paradox of tin.
Yes, the supply chain.
We need this metal for green renewable energy and global connection, but we are completely reliant on a scarce enabler that is scattered across the globe. And just like in ancient times, extracting it comes with heavy consequences.
The materials outline the environmental and ethical dimensions of our modern supply chain in great detail, and it is a very complex reality.
Let's talk about how it's actually mined today, because the document points out we have to look at how tin is geographically deposited.
Right. Because cassiterite ore is heavy and resists weathering over millions of years, eroding rocks wash the ore into rivers where it just settles in the sediment. These are called alluvial deposits.
Which means you don't necessarily need a multi-billion-dollar corporate mining operation with deep underground shafts to get to it.
No, not at all.
You can literally scoop it out of riverbeds and pan for it, much like the 19th century gold rushes.
And that geological reality makes the ore highly accessible, which leads directly to the massive proliferation of artisanal and small-scale mining. This is particularly prevalent in Southeast Asia and parts of Central Africa.
But the reality of that decentralized, informal mining is severe. The sources note that the extraction process often involves dredging river ecosystems, which causes massive habitat destruction.
It disrupts river sediments and drives tropical deforestation.
Right. And because the mining is often informal and unregulated, the runoff creates severe water pollution that impacts local agriculture. It's a massive contradiction.
And the ethical implications of the supply chain are equally tangled. Because these alluvial deposits are so accessible to individuals with basic tools, the artisanal mining sector frequently struggles with severe labor exploitation.
The sources mention dangerous working conditions and the use of child labor in some of these areas.
Yes. And in certain regions, the decentralized nature of the extraction means that armed groups can easily seize control of local mining operations. In those specific supply chains, tin is officially classified as a conflict mineral because the profits from the extraction are funneled directly into financing regional armed conflicts.
So we desperately need this metal. We need it for green renewable energy, and we need it for the global digital connections that allow us to share ideas.
Right.
But extracting it causes severe environmental degradation.
This is the core philosophical dilemma presented right in the source document. Can a civilization built on connectivity ensure ethical sourcing of the materials that connect it?
Tough question.
We are totally dependent on these supply networks, yet the foundations of those networks are fraught with deep moral and environmental compromises.
It really reframes how you look at the concept of a Tier 2 civilization-critical material. Tier 1 materials might be things like water or iron, things you literally cannot live without, or things that dominate by their sheer volume.
Right.
But tin's greatness, its critical nature, emerges entirely through combination.
It teaches us a fundamental lesson about how human civilization is actually built. We tend to focus on dominant materials or powerful, solitary figures, but progress isn't built in isolation.
No, it's not.
The Bronze Age happened because tin was introduced to copper. The digital age happens because tin solder allows microscopic electronic components to communicate. Human civilization isn't built solely by dominant materials. It is built through connections.
I want you to think about that right now. Look at the device you're using to listen to this deep dive. The smartphone in your hand or the laptop sitting on your desk.
It's right there.
That device is physically held together by element 50. When you look at it, you aren't just looking at plastic, glass, and silicon. You are holding the physical culmination of thousands of years of human cooperation, trade networks, and metallurgy. You are holding the invisible binder,
The invisible binder that forces us out of isolation, but also forces us to rely on a massive, complex, global chain of human labor.
which leaves us with a final thought to ponder. As we learn from the sources, when the ancient tin trade routes broke down around 1200 BCE, it may have triggered the Bronze Age collapse.
An entire era of human progress shattered because their crucial supply chains snapped.
Exactly. Today, our entire digital infrastructure from the internet to the power grid to global logistics depends on global tin supply chains spanning oceans, borders, and complex geopolitical fault lines.
It's all connected.
If tin is the ultimate symbol of interconnectedness, it's also a symbol of our fragility. What happens to our modern Bronze Age if the supply chain for this invisible, unassuming binder snaps today?